All right. Thank you for the introduction. Thank you for the very nice talk. Give me 1 second to set up. All right. So I first met Michael when he was in his last year as an undergrad at MIT. He was taking an advanced data structures class that I was TAing for the first time that was set up as an open problem session for the bulk of the class, which was great. So the professor, most of the classes were set up where we give like an easy problem that was solved, like an open problem, and we go around talking with the students. And Michael, as you can see from the G-chats, he was just full of these like short snippets of like, oh, did you know you could improve this way? Here's a much cleaner answer than this. Have you thought about this problem? And there'd always be a mix of like, some of them would just be clean and you would get run of the way. Some were like really good at hooking you, like asking you a question you thought you knew the answer to. And then he would turn it on its head and realize there's something much more complicated there, and he had a really nice answer. This whole class, Michael was full of these things. And this was responsible perhaps for the one maybe not positive TA review I got over the course of the class, where someone wrote at the very end of like, yeah, the TAs are pretty good, just they seem easily distracted by the students who want to talk about some sort of unrelated problems to the material of the class. So that was my first experience with Michael, and it was pretty characteristic of working with him then on. Whenever you'd pick a problem, he would just keep generating these sort of very nice insights all around, and little things to push problems. But what I wanted to tell you about today was, I think, the first time I had a more serious conversation about any of these things with him. It's the first problem I maybe worked with him at all on, and it's a problem I worked with him on and off, I guess, over a number of years since. So the point of this talk is to, tell you, I guess, a bit about the problem, my thinking on the problem, and give you enough information that you can appreciate like the simplicity in what Michael did when he looked at the problem, and get a taste of some of the things he was working on over the last few years that aren't out in the literature, that need to be out in the literature, and some cool things that happened along the way. All right, so that's what the talk's going to be about. So the talk is entitled Michael and Cohen and Oblivious Routing. And this talk will be about Oblivious Routing and basically a bunch of things Michael taught me over the course of the last number of years. All right. For those of you that know Oblivious Routing, well, some of this might be sort of known, but I hopefully want to demonstrate, I think, the simplicity and beauty in some of the things he came up with along the way. All right. So the rest of the talk, the main thing I'll be talking about is Oblivious Routing. This is one of maybe my favorite problems in combinatorial optimization and online algorithms. I guess he had been working on online algorithms for a period of time. And the problem is as follows. So we're given as input some large undirected graph G. So some really large, complicated, undirected graph. Has some n vertices V, m edges E, and some non-negative capacities. Mu. All right. The other thing we get as input to this problem is some sequence of demands. So by demand, I simply mean some vector over the vertices of the graphs. These are d1 through dk. That simply each specify how much flow should enter or leave some vertex of the graph. So the first demand might be 1 in at this vertex, 1 out at this vertex. The demand d2 might mean like half a unit comes in here, a quarter unit comes out here, and a quarter unit comes out here. So demands are just some vectors on the vertices of the graph that sum up to 0, meaning the total amount that should go into the graph should be the total amount that comes out. And the goal of the problem is what we want to output is some sequence of flows, F1 through Fk. over the edges of the, and these flows are simply assignments of real values to the edges of the graph. So they simply specify how much flow goes in each direction on every edge. And these flows have to have the property that the flows, each flow fi routes the demand di for all I. Because I can't help it, at times in the talk I might use this notation B transpose fi to denote the flow routed by fi. So fi is just these real values assigned to every vertex of the graph. To route a set of the demands that a route simply corresponds to, for a flow at every vertex, how much the net flow that goes in and out. And for a flow to route a demand, it means the net flow going in and out should be what's specified by the demands. So for the first demand that was 1 in here and 1 out here, the flow might be some st path that sends 1 unit from s to t. For this one, it might be something that sends half a unit for a while and then splits up into smaller things going in each direction. All right. And our goal is to get the best routing of the demands. Okay. Right. Now, for this to be a well-specified problem, I need to tell you what I mean by best. I have to specify what's the objective under which we want to get these flows routing the demands. And the most common one cited for the Oblivious routing problem is congestion. So this will be our benchmark for how ideally we'd want to route the flows subjects to the demand. And we'll say that for some set of flows, fi, the congestion it has on some edge e is simply the total amount of flow over this edge divided by the capacity of the edge. All right? And we'll say that the congestion overall of the flows is simply the most any edge is congested. And ideally, if we know the demands and we knew the graph and we had all the input, what we want to do is get the flow that routes the demands that has minimal congestion. And I'll denote that optimal congestion by opt of di. And this is simply the minimum over all the flows that routes the demands, the congestion of every one of the flows. All right. So the idea here is we should think like maybe the graph here corresponds to links on the internet. We're getting a bunch of requests, people wanting to get information from different points. And we can't, what we want to have is that no network edge in the network is utilized too much. Right? And ideally, this is what we'd want to solve. So this particular problem of minimizing congestion is also known as the, after scaling, is basically the concurrent multi-commodity flow problem. And in general, it's expensive to compute. You need to look at all the demands and the entire graph. This could be a fairly expensive optimization problem. So what the Oblivious routing question asks is maybe is there some way to solve this problem approximately with a much more simple operator? In particular, what I'll call the linear Oblivious routing problem asks is maybe instead of trying to solve this complicated joint optimization problem, where we look at how these demands interact and try to pick flows accordingly, instead, let's just try to pick a fixed scheme for how we would route every single demand and use that as an approximation. All right? So we call an operator R. That's just a mapping from the vertices to edges. A linear Oblivious routing. If it has the property that it's a linear mapping, it takes as input demands, and it outputs flows, so these assignments to the edges that route the demands. And this is what we'll call a linear Oblivious routing scheme. This is linear mappings from what the imbalance is every vertex to some flow that routes it. So if the demand is 1 in at S, 1 out at T, it might spit out a path or a distribution over paths routing to it. All right, and now the question we want to ask is, if we commit to a linear oblivious routing scheme, instead of solving this joint optimization problem, how good can we get? How well does such an oblivious routing scheme do? And formally, the oblivious routing problem then asks, is there such a scheme that does as well as opt? All right. So can we get one scheme that if we route our demands by R, it does almost as well as one would hope to do if they solve the full joint optimization problem? So formally, we call this the competitive ratio of an oblivious routing scheme. We'll denote it rho of R, and it's simply the largest over every sequence of demands you could possibly get, the congestion incurred by routing the demands using R, divided by the optimal congestion. So how much more do we congest things if we route everything using our fixed scheme that use nothing about the joint sequence of demands we could possibly see? How much larger is the congestion of that as compared to the optimal congestion? Right? So the oblivious, yeah?
So this is defined for a fixed graph with fixed.
Yeah, right. So the oblivious routing problem, Jen, you would ask overall, what's the overall graphs? So this is the competitive ratio in a single oblivious routing. Like once I fix one, its competitive ratio is the worst this ratio can be. And in general, the question is going to be, one, can we always, so for all graphs, find R with a good competitive ratio? And two, can we find it quickly? Okay. So that's the problem. It's the rough problem Michael and I have talked on and off for a number of years in a variety of contexts. And I think what I want to tell you about is roughly how one would go about solving the problem, what the algorithms look like, and his very simple insight that got rid of what I thought was some very needed machinery. So the first time I think he caught me in one of these like, oh, pretty sure there's a much simpler way to do any of this. And hopefully in talking about how you would go about solving this problem, you can get a little bit more of an appreciation, I think, for some of the improvements he shared along the way and was working on we'd always been working on. All right, so that's the question. The question's clear. Can we always find the oblivious routing with a good competitive ratio, and how fast can we find it? All right. Quick aside, why would you want to solve this problem? First, it's just a natural online problem. You can imagine we're only getting the demands one at a time. So we have the internet, we're getting a request to send one unit from S to T, we're getting one unit to send somewhere else. We're getting them one at a time, and we immediately want to respond with a flow routing each of those demands. This is giving a solution to that online problem, because given every demand, you could just route it using R. And how well you would do, the actual competitive ratio of that scheme, like the congestion you get versus if you had done everything with a joint optimization problem at the end, would be given by the competitive ratio. So it's a natural online problem. If it's solvable at all, if you can get a good competitive ratio, it says something very interesting about, I think, the structure of multi-commodity flow and undirected graphs. The answers for this, along the lines that solving this seems like you'd have to have some interesting structural decomposition of your undirected graph. Correspondingly, algorithms for this have been used to get better approximation algorithms for a whole host of problems. I believe the best approximation ratios for graph bisection still go through oblivious routing insights. And I guess the reason I originally looked at it is it's been shown over the last few years, you can use algorithms for solving this to get faster algorithms for solving flow problems. So things like max flow and multi-commodity flow. Okay. Right. Good. All right. So with this motivation in mind, okay, what are the best known running times for solving this problem? There's a long line of work. There's a long line of work on solving this problem. So here I'm going to use T of R to denote the time needed to apply, to compute R and apply it and its transpose. There was a long line of interesting work on this problem. I guess the first time you think about it, one of the reasons I find it exciting is it's not even clear immediately that there is, you can get rho of R to be bounded. You might worry there's some sequence of demands that you keep rigging things up in some weird way to make the congestion on an edge grow and grow and grow. But there was a long line of work showing that not only is rho of R bounded, and you can get competitive ratio, bounded competitive ratio. But after a long line of work that I can't quite do justice to, there was this beautiful result of Reiki in 2008. Showed you can always get a competitive ratio of log n. So you can get that how much worse the oblivious routing does than multi-commodity flow. Grows fairly slowly with a number of vertices. And you can get that you can apply it in a pretty reasonable amount of time. You can get something quadratic in the number of edges. This was improved in joint work with John Kellner, Yintat Lee, and Lorenzo Orecchia to get something where it's almost a constant. The competitive ratio you can apply in almost linear time. But it was, you can do this using some insights of a cool paper of Madri in 2010, but it was horribly complicated.
What if I don't care about the running time?
Then I think this is fairly straightforward if you know how FRT works. And that's what I'll touch on really briefly and motivate why you have to do something complicated and why Michael showed you don't have to do something so complicated. Yeah.
I'm confused about something too.
Yeah.
What T of A is the time it takes to apply this to?
So like the time to look at RD and R transpose E for some vectors D and E.
But isn't it an m by n matrix? Can't you apply it in m n times?
Yeah, but so that's why being able to apply no tilde m is non-trivial. So this is true. Oh, but the time to construct it as well. You can imagine constructing the oblivious routing is very complicated. But good point. The time to apply it, you could bound that way, assuming it's explicit. Yeah?
So what is this O tilde 1? It's a log.
Oh, so it's something. I'm using a double tilde to be something that's between, that's smaller than any polynomial, but larger than polylog. Yeah, I probably shouldn't have just used that off the. It works twice on the whiteboard and horrible in LaTeX. OK. All right, so this is what I want to tell you about, and then sort of the cool work Michael did going off of this down the road. All right, so the question clear, the result clear?
And log n is best possible?
Yeah, this is tight. Yeah, good question. This is tight. You can't do better. Yeah, expanders, sparse expanders. Yeah, any other questions? OK. All right, so how do you do this? So I'm going to go really quickly, I think, through the history of those results, how to do it, so you can see Michael's much, much simpler scheme, which is good to erase. I'm going to erase this. OK, so how do you do this? I think there is two main ideas needed to understand the results. They're fairly short. So the first idea OK, so the first thing, if you want to go to construct these things, you would ask for a routing scheme. How do I actually get a handle on its competitive ratio? Actually trying to go through this formula might be a bit complicated. Trying to reason about the worst case demand sequence gets quite complicated. But using the fact that we restricted our attention to linear oblivious routing, so it's just some linear operator R, you can actually show there's a really short formula for the competitive ratio. It's just equal to this, where U is the diagonal matrix corresponding to the capacities. All right, so now it should all be clear. OK, so what does this actually mean? this is just a very, very concise way of saying the competitive ratio of an oblivious routing scheme is the congestion incurred when you route the graph obliviously on itself. So you fix some linear routing scheme. Now imagine for every single edge, you think an edge just has two endpoints, some A and B. It has some capacity. Imagine routing capacity units of flow from A to B. And do this for every single edge in the graph. Right? So take that as your demand set. That is your demand set obliviously. Look at the worst congestion on every edge. Turns out that's exactly equal to the competitive ratio. And if you think about it, that's what this is a shorthand for. All right? So what this means is, for the sake of trying to bound the oblivious routing, we know the worst demand set. The worst demands are simply when you route every single edge in the graph corresponding to its capacity. So if you think of the oblivious routing as sort of embedding the graph on itself, that's the worst case scenario. And you just need to bound that. All right? So that's the first idea. So this tells us at least what to aim for and how to reason about the quality of an oblivious routing. The second idea that appeared in various forms on the work is that you don't have to construct the oblivious routing all at once. There's ways to compute it by reducing to simpler graphs. All right? So suppose we want to get our oblivious routing for G, and we have some graphs H1 through HK. Right? Now, so these are just some graphs that we're going to try to reduce computing oblivious routing on G to computing oblivious routings on these graphs. All right? Suppose G embeds in HI with for every I with congestion rho I, rho 1, meaning we can take every edge in the graph and map it to some path in HI. Right? And the ultimate congestion incurred when doing that for every edge in G and H is rho 1. Further, suppose we have routings AI for each HI with congestion, with rho of AI equal to rho 2. So for every one of the AIs, we do compute some oblivious routing. And finally, suppose we have some embeddings M1 through MK that take each of them takes the graph HI and embeds it back in G. So every edge in HI gets mapped to some path in GI. All right? And suppose this has the property that if you look at the congestion the congestion of embedding every one of the GAIs with the MI back into so if you look at so we have these embeddings M1 through MK. We have that take every one of the HIs and map them back to G. Now imagine what we do is we look at the graph that's like the distribution over HI. Right? We look at the congestion incurred from embedding that distribution. So for every, we wrap like a 1 over k fraction of every one of the HIs back in the graph. The overall congestion, let's assume the overall congestion of that is rho 3. Right? Meaning like the total expected congestion when routing all the HIs back in G is some number rho 3. All right? So our graph embeds into every one of the HIs, we have good routings. And then the HIs and expectation embed back into our graph. All right? If you have this, then you have that the competitive ratio of simply routing obliviously in every one of the GIs and then embedding back into the graph. The competitive ratio of this is simply the product of these three numbers. Right? What they're saying is you have your very complicated graph. You have a bunch of simpler graphs that you know how to route in. To route your demands here, simply route your demands in each of these, and then embed it back in the graph. And as long as you have these properties, you get a good competitive ratio at the end. Okay. All right. Those tools in hand, that's about the bulk of what you need to understand, I think, how how you would actually go about constructing these oblivious routings. The way Reikio 8 actually worked is they showed that if what you do is you take any distribution over the edges of the graph, so you have some distribution over the edges in the original graph you want, they showed there exists some graph H that depends only on this distribution P, such that is a tree. I'll call it TP. So there's some tree depends only on the distribution of this distribution P that has the following three properties. One, you can show that G embeds into this tree with congestion 1. 2, there is O of 1 oblivious routing on TP. This is immediate. For trees, there's only one ways to route. So just routing on a tree, the only way you could if you want one unit here, there's only one path. There's only one way to route anything. So the trivial routing is always an O of 1 competitive ratio, or 1 competitive ratio. And 3, there is an embedding from TP to G so that the expected congestion on each of the edges when you look at expectation by P, so you pick an edge with probability proportional to P and then look at the congestion on that edge when embedding from the tree back into the graph, you can show that that is O of log n. This is essentially using FRT, very cool result of Rao and Talwar. And yeah, I try to. How do I pronounce it properly? Huh? Factor. Thank you.
Yeah, let somebody else better.
Thank you. Thank you. And the worst case congestion is O of m. All right. So what this means is you have any distribution of the edges. You can get a tree-based routing where the expected congestion on every edge is bounded. It's O of log n. And the worst at any edge's congestion is O of n. All right? So what this essentially is saying is we have our graph. For any distribution, we can find a tree. That inside it, you should essentially think that we can find a tree inside such that the expected congestion is small. But what we actually want, is what we want to have is not that for a fixed distribution the congestion is small. We want to have that, we want to get a bunch of trees such that if I look at the congestion on every edge averaged over all the trees, this is log n. Right? And if you know multiplicative weights, well, this is a primitive. If you play the right game on how you play with the distribution, the median implies this. And the fact that every edge, no edge has congestion more than m, tells you only need to do m trees. And that's essentially the proof. OK, so the big problem with actually running this is that it's rather slow. Right? So this shows that you can get a competitive ratio of log n, but the time is m squared, right? And the time is m squared for a rather fundamental reason. The number, if one tree is congested by m, then if you want to average over a number of trees for nothing to be congested too much, you need to take m trees, right? So even if you just take like a very simple graph of like a bunch of parallel paths, or just m parallel redundant edges, any tree that you pick, you're going to try to route m units on it. It's going to get very congested. You kind of need to take a large number of trees before you get any sort of real runtime improvement. All right. So this is sort of the big bottleneck in trying to make this efficient. There was a really nice, idea of Madri 10, showed a very nice idea. Said, maybe, so the bottleneck here is that however much an edge is congested is going to boil down to the number of trees you actually need to compute. So the idea is instead of trying to compute all the trees at once, maybe we'll try to just compute a slightly simpler object with better congestion. So that we don't need as many, and we'll do the construction recursively. So the idea was still take a tree, look at the congestion incurred when you route every edge over the tree. All right? And now if an edge, and then the idea is simply if an edge is congested, keep it. So keep it and all the edges that go over it in some way. So it doesn't count to your overall congested. And the key idea is that not too many edges in the tree can be congested. So if you look at sort of the bottleneck edges, if you look at these congested edges and try to route towards them, you can show, right, so the idea is to take the congested edges, try to route all the edges not in the tree towards these congested edges, and reduce it to some graph where the edges are only incident on the congested edges. And if you do this carefully, you can bring down the congestion, and you can show that you can recurse. Instead of needing to compute oblivious routing on M graphs, you can show that you need to only reduce on KM graphs for any parameter k with O of m k vertices, right? And to actually make progress, you sparsify the graph so that m is on the order of n, and argue you can always recurse on a smaller graph. All right. So the big problem in doing any of this is sparsification. So when we wanted to try to use any of this to get oblivious routing, this was the big bottleneck to overcome. That somehow you sort of needed to sparsify a graph so that you can turn average congestion onto tree into average congestion only around a few vertices and have something smaller to recurse on. So the way we got around this is we had a very, very horrible solution where we showed that what you can do is you can break your graph. I'll just say it out loud, actually, because I'm running a little low on time and I want to talk more about Michael's work. To get around this problem, we had a complicated thing where we said, take your graph. Right? So the problem we have is that we have a dense graph. We want to sparsify it and reduce constructing oblivious routing on the dense graph to constructing oblivious routing on a sparse graph. So what we did is we showed a very complicated scheme. We broke the graph into expanders, showed you could subsample edges from every expander, route the expanders back on the original graph using electric flows, prove some properties about electric flows on the electric flows within subsets of expanders, do this with the right recursion and the right subset of expanders property, and it solves that subproblem. All right. So this happened some point earlier in grad school. I don't know. I was pretty proud of it. I'm not sure if Yentet feels the same way. And there I am talking with Michael. I think he was there for prospective student visit days to decide where to go to grad school. And he's chatting casually about the paper. And I think the phrase they said, it was something like, I'm sure you've all heard this, something like this. It's like, you know you don't need that, right? There's like multiple pages of complicated analysis. He's like, yeah, to get around this issue of like sparsifying, yeah, don't do any of that. He said, just sparsify the graph like you normally would. And normally the way you do that is you just pick every edge with some sampling probability. Like there's a sampling probability for every edge. You sample by that, you get a sparse graph. He's like, yeah, I know you're worried about these issues then of like how you embed it back and forth. So to get around that, just make sure probability edges included is at least some like 1 over k. Pick like some parameter, like whatever parameter of how much you're trying to decrease things. Just make sure you don't pick any edge by too small an amount. Right? This won't solve your overall problem of, can you reduce solving on a sparse graph? But this will let you decrease the number of edges in your graph by a factor of k and make all the progress you're trying to make. So that works out just fine. if no edge is larger, it embeds, if no edge is too much larger, it embeds back pretty trivially, and that all just works out. But it was kind of like a sentence or two, and we went back and forth many rounds until I could see it. So then he didn't stop there. So he said, OK, so good. So all this flow sparsifier stuff of dealing with sparse graphs you don't have to do. And then he also, soon after that, went back through this entire framework. And the reason I presented it this way was he showed is actually all of this stuff, it works not just in the case when you're trying to minimize the worst congestion on any edge, but if instead your optimal congestion, if instead of opt being the sum overall, sum over all the flows, like the L infinity norm of the flow, the largest on any edge. Suppose you want to make this the P norm. He's like, yeah, you can go through this same framework and make it work out. This becomes the P norm, which was something we knew but hadn't wrote about. But then he showed the much cooler one that you can still actually make this type of reduction framework go through, which if you try to think about it a little bit, I think is rather non-trivial as, this picture that we had of always knowing the worst case set of demands that you would want to route doesn't quite work through for the P norm. You have to come up with some other proof that your oblivious routing is good with respect to the P norm. This was known that there were good O of log n competitive ratio oblivious routings for all P norm, but he showed you can kind of get it through the same framework, and the same flow sparsifier stuff worked out. He also did some really cool stuff when we chatted about more, explored what norms you can actually get good oblivious routings for. I think we had a whole bunch of conjectures about what this property the norm would actually have for an oblivious routing to exist, and he ruled out some of them. But it didn't happen over GChat, so I haven't been able. I have some people I need to hunt down to figure out what he did. And then I guess I'll never know if he did this, if it genuinely showed up or did it out of kindness. He might have seen that I was a bit disappointed that you didn't need to use any of this flow sparsifier machinery. So then we're talking about polishing all the boundaries of everything and trying to get oblivious routings very efficiently for all P norms. And he had a nice idea to do flow sparsification in arbitrary LP norms, and a sketch of why you could do that, and arguing why you might actually need this sort of sparsification machinery. And I think one of the highlights of talking with him about this is we're talking about how you would maybe prove that things work, and out of nowhere he's like, oh yeah, just use Cheeger inequality in the LP norm. I'm not sure it's part of the literature, but he had a way of modifying everything so that you had Cheeger inequality in the LP norm. And it was said as like a quick aside in some conversation that then was like many times chatting with him to actually work out. He also had ideas for flow sparsification to give faster running times through a framework of Sherman to get even faster flow algorithms for different LP norms, which I thought was rather clever. And all along the way here, I guess this idea that he would try to really hone in on what machinery was actually needed, what actually made it work, and finding sort of the cleanest perspectives in which to get proofs was very characteristic of his work all around. If I had more time, I think even beyond the list of talks there are today, there's all sorts of contributions he made. There's a whole line of work he did on geometric median. I think that was one of my favorite meetings with him, where out of nowhere this problem went from looking like it might have some structure to looking like it would be very, very easy. A whole bunch of things I wish I paid better attention to when I was TAing on the first year, when he talked about LP norms, and a whole bunch of stuff on how you would sample cycles from directed graphs. The list goes on and on and on. Sorry, I'm a little over on time. Thanks.
Quick question.
Okay.
What does Cheeger inequality in the LP norm mean?
Yeah, he had like an LP norm Rayleigh quotient. I can talk to you about it afterwards. He had a way of like bounding like LP operator norms from cut properties. Yeah. Thanks. Yeah, happy to talk about that more.
Whiteboard also?